Edexcel Core Pure First Order Differential Equations. Integrating factor. Multiplying by a factor to give a perfect derivative. So if we look at a first order differential equation, we say that it is linear if it can be written in the form dy by dx plus py equals q. P and q are both different functions of x, and we need, for it to be linear, we need both the power on the dy by dx and the power on the y both to be 1. So if we can write the differential equation in this form, then we say it is a first order differential equation and it is linear. So if we look at this first example and explain why this one is linear, I can rewrite this as dy by dx plus minus x squared y equals x squared. So this term here is the p of x, the function of x. This term at the end is the q of x. And notice that I've written it deliberately to have a plus sign. So this one can be written in the appropriate form and therefore is a linear first order differential equation. This one isn't linear. If I try and rearrange it to dy by dx plus minus y squared equals x squared, we can see here that this is not linear. Although we've got a function of q on the other side, this minus y squared is stopping it being a linear differential equation, and therefore this one is not linear. If we now look at something like dy by dx plus 1 over xy equals x squared, now I'm going to take this and I'm going to multiply both sides by x. It may not be obvious why at the moment, but all will be explained later. If I multiply through by x for this linear problem, I get x times dy by dx plus 1 times y equals x cubed. And you may, particularly if you look at this left hand side, you may have seen things like this before when you've done implicit differentiation of a product. In fact, this left hand side is the derivative of a product. So if you focus on this left hand side, then we can rewrite this as the derivative of a product, and that product would be x times y. So this is leave x, differentiate y, plus differentiate the x, leave the y. So this is the derivative of xy with respect to x on the left hand side, and on the right hand side we still have x cubed. So now we've got the derivative of this product xy equals x cubed. So now we are in a position where we could integrate both sides with respect to x. So before we integrate both sides with respect to x, the key step was I multiplied both sides by x, and the reason I did that was to make this left hand side into the derivative of the product xy. So the derivative of the product xy, the derivative with respect to x, is equal to x cubed. So now we're in a position where we can integrate both sides with respect to x. So the more formal way of writing this would be to put the integral of the derivative of xy with respect to x is the integral of x cubed with respect to x. So that's the formal way of integrating both sides with respect to x. If we look at the left hand side, if we integrate the derivative of xy with respect to x, then we should go back to xy is the integral of x cubed dx. So this more formal line of work in here can be omitted quite safely, and we can go straight from the derivative of xy equals x cubed straight to xy must be the integral of x cubed dx. In other words, xy is a quarter of x to the 4 plus c, and if I divide through by x, I get a quarter of x cubed plus c over x as my general solution. Notice this was a first order differential equation that we started off with, and we've ended up with one arbitrary constant c. So this is the formal step where we've integrated both sides with respect to x, and if we integrate the derivative of xy with respect to x, then we have to go back to xy. So it's perfectly acceptable to go straight from that line to that line, and this formal line of working can be missed quite safely. So we've ended up with our general solution, and we've got our constant, arbitrary constant c. So now we can introduce the idea of an integrating factor. In this particular example, I multiplied both sides by x, and that is called the integrating factor. So multiplying through a differential equation to make the left-hand side into a perfect derivative requires the use of an integrating factor. So in this particular question, I knew that the integrating factor needed to be x. So what we need to look at in the future video is how do we know what the integrating factor needs to be and for a particular problem. Once we've used that clever integrating factor and written the left-hand side as a perfect product, it means that we can then solve the problem by integrating both sides with respect to x. And that integration process will introduce one arbitrary constant for a first order differential equation. So in the next video we're going to be looking at how do we find the appropriate integrating factor.